I'm Dr. Allegra Lieberman-Martin, a chemistry professor, and I'm excited to be moderating up until the break this morning. We'll be having 4 speakers, I believe, for the break, our first of which is Emma Kocik. And Emma has been working for the last year, I believe, in the KEG lab and is going to tell us about sulfate effects on absorption and retention of metals within oxy. I don't want to say the whole title, but it's in case you want to say it. So thank you, and I will give you a 2-minute warning.
Okay. Yes, hello, I'm Emma. As mentioned, I work with Dr. Kim in the KEG lab, and today I'm going to be talking about the absorption of metals to iron minerals in the environment. Oops. So to begin, as you all are probably aware, California as a state was built on mining. We started with the gold rush, and although many of these mines are now shut down, we still face a lot of impacts from them. Here we have pictured the Iron Mountain Mine. It is located in Redding, California. This is a really interesting case study for chemistry. The mountain itself is made of iron sulfide, and the mine was mined for a lot of precious metals that are still remaining in very concentrated amounts. And with the presence of precipitation and oxygen gas, we see acid mine drainage form. Essentially, that's this little red color here flowing into the stream. And that's a very highly acidic, heavy metal rich fluid that is flowing in. And as you see, through sediments and various runoff, flows into various reservoirs and eventually into the Sacramento River, which, as you can imagine, if you're a local resident, that you do not want that in your water supply, and also it poses a lot of health risks to the overall ecology in the area. So iron oxyhydroxides are effective sorbents of metals in natural environments. They form readily in these acid mine drainage environments. And they're the predominant reactive mineral phase in these environments, meaning that when you have ions floating around, they're what are going to sorb it. They also aggregate rapidly under various geochemical conditions, meaning that they're not just floating around as singular nanoparticles, but they're coming together in our environments. And as said, they're effective sorbents, largely due to their small size, high surface area, and thus high surface reactivity. This picture here is acid mine drainage. You see that red color flowing through a stream. So anions, essentially negative ions, impact metal adsorption to iron oxyhydroxides. So a previous study in our lab looked at the impact of chloride to metals already absorbed to iron oxyhydroxide nanoparticles, essentially to model what happens, asking the question, what happens when these particles flow from fresh water into salt water? Are the metals going to be released, retained? And what they found is that chloride enhances the retention of copper and zinc to iron oxyhydroxides. So sulfate is another anion that's really common in acid mine drainage environments, as well as many natural aquatic environments. You can see here a couple of examples of where it's found. It's the second most common anion behind chloride in seawater. It's found in ultrasaline lakes and in high concentrations in acid mine drainage, such as Iron Mountain, as an extreme example at 2 molar. So this kind of led to my research question, which was, how does sulfate concentration influence the adsorption and retention of zinc to iron oxyhydroxide by nanoparticles, and by what mechanism? So the first thing we did in our methods was we synthesized the iron oxyhydroxide in-house using a flash microwave synthesis that is well described in the literature. There's a few pictures of synthesizing these in the lab. After they've been made, they're allowed to equilibrate in these little tubes for about a week, and that's how we synthesize our iron oxyhydroxides. Next, we aggregate them because, as mentioned, nanoparticles don't just stay constant, but they aggregate under different conditions. And so essentially, we aggregate them by either raising the pH, raising the ionic strength, or raising the temperature. All of these things bring the particles together and form aggregates with different structures that mimic potential aggregates that might be found in the environment. So these are all the aggregates that were made for this experiment and were tested. Next, we have our absorption experiments. So this was the bulk of the experimental work that was done. The first thing we did was we combined our zinc with the iron oxide hydroxides, the various aggregates. So so you have your metals here. The pH was brought up to 7.5 because that was shown to bring about maximal adsorption. That gave us our adsorbed sample. Next, sulfate was added in varied concentrations to the sample, and this was allowed to sit for 8 hours. So that gave us this adsorbed sulfate added sample. Finally, we brought the pH down to 5, and we used that as an assay for assessing retention strength. Essentially, that takes off the weakly bound zinc and only leaves behind the strongly bound zinc, and that's what's known as our retained sample. Finally, all samples were centrifuged to separate out the nanoparticles from the supernatant. The supernatant was prepared for ICP-OES, and the solid nanoparticles remaining were prepared for EXAF spectroscopy. So ICP-OES is essentially an instrument we have here in Keck that can be used to measure the concentration of metals in solution. So for this case, we used it to calculate the percentage of metals adsorbed and retained to the nanoparticles. Next, we used EXAF spectroscopy at the Stanford synchrotron radiation light source, and this is used to determine the local environment around our zinc. So essentially, we can look at our samples in this using high-powered X-rays and see what is surrounding our zinc atoms and how close these other atoms are. Finally, we paired this with geochemical modeling, essentially to determine the metal speciation in a model solution using the GeoChemist Workbench software. So moving into our results. Our first results here, to orient you on the plot, this is for control nanoparticles. As we move from left to right and increasing darkness, this is referring to sulfate concentration as given by the legend here. The gray bars refer to the adsorbed portion of the sample. So that first section of the experiment where we upped the pH and adsorbed metals on, whereas the orange hues here refer to the retained sample. So after we drop the pH down to 5, this is referring to that strongly bound zinc remaining. So a couple key things to take away from this. First of all, we see an initial increase between 0 and 0.03 molar sulfate of about 5%, and that falls within, we have low errors here, so that's pretty certain. And then we see a relative stabilization even as sulfate increases. However, for our retained sample, while we do see that initial same jump between 0 and 0.03 molar sulfate, we see a continual gradual increase in retention of zinc to the particles as a function of sulfate. And now, after a little bit more lab work, we have data for all of our aggregates that were tested. And the interesting thing here to take away, although the absolute percentages of adsorption and retention are different, the relative trends remain the same. We see that same initial jump between 0 and 0.03 molar sulfate in adsorption, and then that significant continual climb in retention as a function of sulfate. Next, moving into our modeling results. So the main thing to take away from our modeling is that the parameters are given, but the concentration of zinc is representative of that in the macroscopic experiments. And the amount of sulfate, sodium sulfate added in was in the same concentration as our macroscopic experiments. So we're asking the question here, without the presence of our iron nanoparticles, what would the speciation of zinc be in solution? And so from here, we see that zinc sulfate increases in concentration to about below 0.01 molar sulfate, and it stabilizes at that point. And so the main thing to take away here is that our free zinc ion is in the same concentration as zinc sulfate by that point of sulfate, 0.01 molar, meaning that we should be looking out for zinc sulfate interactions in our EXAFS results as a significant interaction. So moving into our EXAFS results. Here, to orient you, this is what's called a chi plot, and this is what's called a Fourier transform. And what we see is first we tested the adsorb followed by various sulfate concentrations. And now the main thing I just want you to take away from this is that we see structural changes in the spectra. So you see this peak sort of separate, and that's seen in our second peak here as it starts to get bigger. And that data can be fit using a software called SixPack to various shells. So we look at paths of zinc oxygen, zinc iron, zinc sulfate scattering paths that are predetermined, and we can fit our data to those existing paths. And so to break this down, I made a conceptual model of our adsorbed sample pre-sulfate addition. So this is before we add sulfate, what we see surface zinc complexes being dominant. So what the squares and numbers correspond to are our zinc iron coordination numbers. Essentially, it's telling you how many iron atoms are around every zinc. So our zinc atoms are the blue circles and the iron are the red squares. And so we see mostly 1 to 2 coordinated surface complexes through our fitting. Next, when we look at the desorbed sample, we see that zinc incorporates further into the nanoparticles and sulfate bonds to the remaining surface zinc. This was determined by the ability to fit a zinc sulfur shell, which is represented by these interactions where you see iron, zinc, and then sulfate all binding together. Also, we're not really able to determine what exactly is happening within the structure, but the increase in coordination numbers with these samples indicates that the zinc is burrowed further into the sample as opposed to being surface bound, essentially indicating that we have a more strongly retained, strongly bound sample, which would be less likely to release metals into aquatic environments. And finally, we have our desorbed sample of greater sulfate concentrations, and we see exactly the same structure. You're seeing no structural changes between the earlier sulfate concentrations in this sample, but we did see a decrease in coordination numbers with zinc and iron. So what that likely indicates is that we have more free zinc and sulfur floating around and interacting, and that's going to have a coordination number of 0 because it's not interacting with the iron, and thus X-DOPS takes an average of all the bonds in our sample, and so that's likely skewing our results downward. So all that, what does it mean? Essentially, we see that sulfate increases the retention of zinc to suspended and aggregated iron oxyhydroxide nanoparticles. We also see that the mechanism likely involves ternary surface complexation. So that was what we saw where we had our iron nanoparticles with zinc bonded and then sulfate bonded on top, which is relatively novel. And we also, this is good news because if we have metal sorbed iron oxyhydroxides, they are unlikely to release sorbed metals back into the environment when entering other sulfate-rich ecosystems. There is more research on the way. I will be sticking around this summer. So I will be completing this data set for copper, as well as conducting experiments with artificial seawater as the salt source. This is actually just this past weekend. We went up to Stanford and we're collecting data for our artificial seawater samples. So that's super exciting. This here is the cot where I took a couple great naps on. But yes. These are my acknowledgements. I'd like to thank the various funding sources, Dr. Kim for his help on this work, as well as many miscellaneous thank yous for throughout this major and getting through it all. Thank you, and I'll take any questions. Yes.
So at the beginning, you mentioned that there is a deposit up in Northern California, and that there's mine drainage from that site. What's the pH of that mine drainage water, and does that relate to the pH that you were operating within in your experiments?
Yeah, so Iron Mountain's actually extremely interesting because it's an extreme example. The actual drainage within the mine is like negative pHs, like it's absolutely insane. However, the drainage we're looking at and the sample conditions we're looking at metals that have flown out and are now in aquatic ecosystems. So it's way less concentrated and you're getting to a more normal, like, environmental pH that's like neutral pH. Yeah. So that's kind of what we're attempting to model with our experiments. Yeah.
Bringing me back to my lab days. It's a broad question, and I'm not sure if you're gonna know this, but there was a graph that you had a temperature difference. At the warmer temperatures, you were seeing that sort of change. Do you think that could be something in the future that should be investigated because of global warming and temperature in the waters rising? I'm not sure if that's too far out, but I'm just.
No, I think, so the temperature, if we went back to the 75-degree aggregates you probably were thinking of were like a lot lower in absorption. And we think that's because a lot of past studies in the lab showed that these aggregates at higher temperatures have the least surface area, so there's the least available spots to bind into. However, 75 degrees is so high, it's kind of more as a, I guess, proxy for developing different types of aggregates as opposed to modeling what's actually happening in the environment. We're just trying to create aggregates of different structures. So I don't know, but it probably will be less significant than that, yeah.
A couple more hands over here. So you said that you were gonna continue over summer for copper research. So like, what do you hope to find, or like, what questions do you plan to ask that might be different than this kind of path?
Yeah, so we've actually started on the copper research. It's just that data set is less complete, and that opens up, that like basically doubles the presentation length because you're going over two metals. And we've seen so far with the preliminary research, less of that ink. As you can recall, as a function of sulfate, we saw like that straight kind of line going up of gradual jumps. And with chloride, we saw kind of more of a stabilization and a less clear trend. So it's probably going to be a little bit more difficult to decide. But yeah, we're same questions, just different metal.
Did I see one more here?
Oh.
Just a little more simpler, but what did you use the dissociation so it didn't interact?
We used like sodium hydroxide to bring the pH up and nitric acid to bring it down. So we already had in our samples, if you can recall back to the aggregate graph, we had a background ionic strength of about 0.001 molar. So we had some background like nitrate ions and things present. So it doesn't shift it too much.
Wonderful. Please join me in thanking Emma for a wonderful presentation. Well, our next speaker is going to be Alexa Wilson. Alexa is a chemistry major and has been working in my research group with me and with Dr. Zach Demavamsi, who's a GCI postdoc. And today Alexa is going to tell us about work using zinc, sticking with our zinc theme from Emma's talk, as a catalyst. And I'll give you a 2-minute warning once we reach 10 minutes.
All right, so yeah, today I will be presenting on alkyne hydrosylation using cationic zinc-fish triple complexes, which is a mouthful. So silicon is the second most abundant earth element, second to carbon, and it is used in products every single day that we all use. And they're developed through catalytic hydrosylation to make silicon polymers, such as this one. Some of these products include rubber wristbands. It's in materials such as glasses and plastics, in resins that strengthen paints and clays, and in adhesives like on the back of sticky notes. This is important because the catalyst used to produce the silicon polymers has a metal center of platinum. Platinum metal center catalysts are very efficient, but they are very expensive and environmentally damaging due to the mining of a heavy metal, and it can be quite toxic and high exposure. Platinum also costs $900 an ounce, which is a lot. So the question becomes, what is a safer and cheaper way we can still make our silicon products with a different catalyst? And that is the goal of ion research. It's to replace platinum metal centers with zinc. Zinc is a much better metal center for catalysts because it is earth abundant, it is non-toxic, and it's inexpensive at 12 cents an ounce. So today I will be presenting the initial process into getting into the entirety of the process of replacing platinum with zinc, starting with synthesizing a catalyst, making a working catalyst by adding 2 or more simple materials to make a more complex product, and testing the efficacy of the catalyst in catalysis, which is the acceleration of the rate of reaction, and then characterizing the products of the catalysis with nuclear magnetic resonance spectroscopy, which will analyze the products to observe the molecular structures. So as I said before, we're making the catalyst using synthesis, and here I am synthesizing this triphenylide acid, which is this compound right here, with this pentafluorophenyl zinc to make the proposed catalyst on here on the left. We are interested in the bistriphenylide acid because it forms a weakly coordinating anion, which gives zinc its catalytic abilities, as well as it has not been used in many cationic zinc researches before. The secondary phenyl group with the fluorines on for the zinc, they do get deprotonated by the hydrogen from the bistriphenylide acid. So as you can see, it's not in the catalyst. It gets filtered out before the catalyst is dried, and it has a very high yield, which is really important because then you don't have to use as much material. To characterize the proposed catalytic product, which is pentafluorophenylate bistriphenylide. I'm tired of saying that. We use fluorine NMR, which determines the location of the fluorines on the catalyst. So here on the anion, these fluorines are located at -78 ppm, followed by on the cation, fluorines at -18 ppm, fluorines at -152 ppm, and fluorines at -160 ppm. And the fluorines that are more downfield, which means closer to 0, are the ones that are closer to more electronegative atoms like oxygen and sulfur. So then we use the catalyst in catalysis, which is increasing the rate of chemical reaction by adding a catalyst. So our catalysis is essentially taking two materials like A and B, adding a catalyst to form an intermediate, and then use that intermediate becomes the product. It kind of glues the two AB to make product AB, but the catalyst is not used in the reaction at all. Therefore, it is not within the product. The type of catalysis we will be using is alkyne hydrosilation, which is the addition of silane over a triple bond to make a variety of products with different configurations. So here's the first hydrosilation reaction I conducted. I added triethylsilane with 1-octine to create a product. And while the reaction was going, while it was reacting, we took proton NMR at 15 minutes, 30 minutes, 1 hour, and 1 day. Proton NMR is similar to fluorine NMR, in which it locates the hydrogen atoms on the compounds instead of fluorides. So here you can see I keep the green colored peak here, matches the hydrogen from this 1-octane. That is how much of the 1-octane is left in our products after 15 minutes. And then these peaks here in purple and blue are from our product. And you can see it's just forming while the 1-octane peak is at 18%, which is this number here. And then at 1 hour, you can see the 1-octane peak significantly decreased from 18% to 2%, and the product peaks increased vastly. And here's a side-by-side location, so you can see how small this really is, which is really nice. So after about 1 hour, we concluded that this reaction completely reacted with 1 day, which is what we use to complete our silane scope. So in the silane scope, we reacted 1-octine with 6 other silanes to determine which silane would be the best silane for our substrate scope, which will determine the the actual efficacy of the catalyst. This was like a pre-scope. So here you'll notice that the larger, bulkier phenylsilanes had lower conversion rates than smaller ones. Then secondary silanes had also lower conversion rates than their tertiary counterparts. And secondary silanes are silanes that have 2 hydrogens on them instead of 1. Tertiary silanes are the silanes that have 1 hydrogen. And secondary silanes also formed multiple products. And we would not like multiple products because it makes our spectra very complicated. And so we would like a single product spectra. So we went ultimately with the high conversion rate single product triethylsilane, which was expected because it had a 98% conversion rate. So then we proceeded to keep the silane constant, triethylsilane, and then change the substrates, just a variety of alkynes. And here we are comparing methyl positions. So the 4-ethanol-toluene has a methyl group in the para position, while the 3-ethanol-toluene has a methyl group in the meta position. And while the difference in conversion rate is very small, it is noticeable that the meta position did have a higher conversion rate than the para position. Then we tested the internal alkyne versus terminal alkynes. Internal alkynes is just an alkyne functional group within the compound versus the terminal one at the end. The 1-phenylpropyne is the only internal alkyne we tested, and it did not do very well with a 3% conversion rate in an hour and 35% in 1 day. While 3-phenyl-1-propyne was a terminal alkyne, the phenyl group was in a different position. It was on the end instead of in the middle, and also had a lower conversion rate than the rest of our terminal alkynes, but it did have a higher conversion rate than 1-phenyl-1-propyne. Then we did an electronegativity test, which was comparing fluoro, chloro, and bromoethanolbenzenes. So the more electronegative atoms did have higher conversion rate than the lesser electronegative atoms, seen with fluorine at 87% after a day and bromine at 71% after a day. So although we did not achieve the complete replacement of platinum with zinc metal setters, we did make significant progress. And now we can do a mechanistic study to further analyze the interactions between Lewis bases and cationic zinc, compare the platinum catalyst with the zinc catalyst results, and finally prove that zinc is obviously the better metal center, and complete a new substrate scope with new functional groups such as aldehydes and alcohols. I would like to thank Dr. Lieberman Martin and Dr. Zach Zamavongzi for presenting me with this wonderful research opportunity and being my mentors for the past 2.5 years and reteaching me organic chemistry multiple times. And all of you for coming to listen to my presentation today.
Use an internal standard to get your conversion percentages, or did you integrate using starting material versus product?
I did both, actually. Yeah. The internal standard had a lot of carbons and hydrogens on it, and it would have complicated the structure.
You add it at the end.
I did,
Okay.
yeah.
That's what we do with a lot of. Other questions? Yes, Dr. Agba.
Yeah, so do you mind going back to the substrate scope slide?
Yes.
What's the major products? Like for all of these, what are the major products of the reaction?
For most of them, they were the E-trans alkene products of the combination of the substrate with the triethylsilane. But some of them did form multiple products, and I would have to deeply go and analyze those.
I'm just curious, which ones were like from the most cleanly E-trans products?
Most clean. 3,3-dimethyl 1-butyne had a very nice clean one. Both of the ethanol toluenes had a pretty clean one as well. I had a bit of trouble with the electronegativity ones.
Yeah.
Yes. But those are from what I recall.
Very cool. Cool. I just one more question about it. So if you don't have the catalyst at all, do you get any conversion to the alkane product?
So we did do a control one with the octine and triethylsilane, and it had a very low conversion rate. So just adding the catalyst to have it fully convert was just kind of a really huge thing. And then we didn't necessarily do the exact same test with all of the substrates, but we did do the one.
So there is clearly a big
Yes.
advancement with the catalyst. Thank you. Yeah, I'll be interested to see your mechanistics. Oh, not yours, but see what is doing. Great job.
Any other questions for Alexa? Okay, if not, we have a little bit of time, so I have a question. I know your least favorite solvent is pentane. What is your most favorite solvent? And deuterated or regular?
For synthesizing the catalyst, or okay, for
Well,
synthesizing
for it across the board.
for across the board.
Big
Okay.
picture.
For analyzing these results, it's deuterated dichloromethane. For synthesizing my catalyst, it's still pentane. Like, it's awful, but it works. Like, it does its job.
Okay. Okay, deuterated dichloromethane, a classy choice. Join me in thanking Alexa one more time for. All right, please join me in welcoming our next speaker, Liam Sullivan, who is also a chemistry major and also working in my research group. And Liam is going to be talking about hydrosilylation, similar to Alexa, but of a different molecule and with a different type of catalyst called the carbodiphosphorane. So, Liam, take it away.
My name is Liam Sullivan, and I will be presenting on ketone hydrosilylation by a cyclic carbodiphosphorane catalyst. I'd like to start off by talking a bit about what catalysis is. Catalytic productions make up roughly 35% of the world's GDP and include things like the synthesis of fuels, plastics, pharmaceuticals. Many things that are produced on an industrial scale will undergo catalysis at some point during their production. Catalysts function by decreasing the energy needed to go from reactants to products. By lowering the energy of this transition state, you can do a few things. Firstly, you can increase overall conversion percentage for the reaction. And secondly, you can increase the overall rate for the reaction. This is beneficial for multiple reasons. A bit more about catalyst background. Catalysts typically function using transition metals. Some very common transition metal centers for catalysts include this group of 8 metals here. Now, rhodium, palladium, silver, gold, platinum, and iridium are all very good catalyst centers. However, they're all very expensive. And so if your goal is a cheap catalyst, these are not for you. This leaves cadmium and mercury, which are very cheap and abundant, but they're also toxic to humans and the surrounding environment. So if your goal is a safe catalyst, they're also not for you. That takes our attention to safer and abundant compounds like the organic molecules, particularly molecules containing carbon and silicon, in part due to their abundance. Carbon is very common and cheap, coming in at 12 cents per kilogram, and silicon coming in at $1.70 per kilogram. Now, a bit about hydrosilylation by our carbodiphosphorane catalyst. Ketone hydrosilylation is used industrially in the synthesis of alcohol products, and it involves the addition of an SiH bond from a silane group being added across a CO double bond, in which the silicon group bonds to the oxygen and the hydrogen bonds to the central carbon. Nucleophilic catalysts have already been shown as effective in ketone hydrosilylation reactions, and because of this, we believe that our cyclic carbodiphosphorane structure will be effective for these reactions. Looking at our structure here, we see that the 2 double bonds joining the carbon to the neighboring phosphorus groups can break through resonance, leaving 2 lone pairs on our central carbon. This creates a very nucleophilic site, which allows for the catalysis of reactions like this. Our goal is to determine the efficacy of our cyclic carbodiphosphorane catalyst in ketone hydrosylation in comparison to other nucleophilic catalysts. A bit about our experimental methods. All of our reactions were performed within a nitrogen-fused glove box environment and were performed at room temperature. Any temperature-sensitive compounds were stored in a freezer within that glove box. Results were analyzed using a nuclear magnetic resonance spectroscopy instrument, and we collected proton, carbon, silicon, and phosphorus NMR for analyzing our results. For the majority of our results, we compared the starting material ketone proton NMR structure to the product proton NMR to determine reaction conversion and whether or not there was starting material present in our product. We used an internal standard of hexamethylbenzene coming in at 2.1 ppm, an integrated disk against our product peaks located here and here. This was able to give us accurate conversion percentages for our reactions. A bit about our catalyst synthesis. The first step was an alkylation step, in which the lone pairs on the phosphorus groups would attack the carbons here, knocking off the iodines and giving us our closed ring structure. This closed ring structure is referred to as our cyclic carbodiphosphorane. Next, there's a deprotonation step, in which the two remaining hydrogens still present on the central carbon are taken off using a strong base. This results in the electrons participating in this bond to move back, forming double bonds between phosphorus and the central carbon, and through resonance, giving us our double ylid form. A bit about the substrate scope for this hydrosylation reaction. The general reaction used acetophenone while varying the silane structure using 5 mol% of our cyclic carbodiphosphorane catalyst. Reactions were performed for 1 hour before proton NMR spectra were taken. We tested a total of 16 different silanes and found that a group of 4 were the most effective. Phenylsilane was very effective, coming in at 89% conversion. However, phenylsilane had a tendency to form multiple addition products, making spectra difficult to interpret. There was also diphenylsilane, which was shown to be more effective than phenylsilane. It did form single and double addition products, but the spectra were more easy to interpret, and the single addition product was preferred in most cases. Triphenylsilane was also shown as effective, though slightly less effective, with a conversion of 73%. We believe the discrepancy is due to the added steric hindrance that the presence of the third phenyl ring gives to this silane. Because of the presence of phenyl rings on our carbodiphosphorane catalyst, steric hindrance can really lower the conversion percentage for this reaction. We also tested methylphenylsilane, which was shown to be effective. It formed single and double addition products as well, but because it was lower in conversion percentage than diphenylsilane, we preferred diphenylsilane for our reactions. A bit about the ketone substrate scope for this reaction. The general reaction used a varying ketone structure along with diphenylsilane in an excess of 1.6 equivalents. We found that an excess of our silane would help react the ketone fully and ensure that there was less starting material in our products. We reacted these at 1 mol% with our cyclic carbodiphosphorane, and these were reacted for 15 minutes before proton NMR spectra were taken. There were a total of 21 ketones analyzed, and the general trend seen throughout these reactions was that electron withdrawing groups present in the para position to the ketone structure increased the overall reaction conversion percentage. However, if the electron withdrawing groups were too bulky or too electron withdrawing, they actually lowered the overall conversion percentage. We believe that this is either due to steric hindrance caused by the bulky groups or an interaction between the electron withdrawing group and our catalyst. Yeah, that's bad. For our nucleophilic catalyst comparison, we tested using acetophenone and diphenylsilane, both found to be very effective in this reaction through our substrate scopes. We used a slight excess of 1.1 equivalents, and these reactions were run varying the catalyst structure at both 5 and 1 mol%. For the catalyst structures, we tested at 5% for all of them, using a cyclic carbodiphosphorane, an acyclic form of our catalyst, a single ylid form, double ylid form, and a nitrogen-containing catalyst that mimics our double ylid. At 5 mol%, it was clear that both our cyclic carbodiphosphorane and the acyclic version were very effective in this reaction, reaching nearly 100% conversion for the acyclic and 94% conversion for the cyclic carbodiphosphorane. These reactions were run 3 times, so what you're seeing here is an average, and the tolerances are the deviations. We also found that the single illid form was somewhat effective at 5 mol%. However, the deviation was 13%, making it an unreliable catalyst for this reaction. Moving to 1 mol% for our effective catalysts, we found that our cyclic carbodiphosphorane was still performing very well, reaching 92% conversion, still within a 1% tolerance, so very reliable. However, our acyclic form reacted at 1 mol% to form 25% conversion with a much larger range, being 11%, meaning that it's a less reliable catalyst, not only having lower conversion percentage. This was likely due to the added stabilization that the closed ring structure provides for our cyclic carbodiphosphorane catalyst. That closed ring structure would provide added stabilization and allow the catalyst to keep reacting even at these low mole percentages. In conclusion, cyclic carbodiphosphorane was found to be effective in ketone hydrosilation with silane groups that had phenyl rings present on the silane, increasing the overall conversion percentage, likely due to inductive effects caused by the phenyl rings. Ketone groups with electron withdrawing substituents present in the pair position showed overall increased conversion percentage as well. And our cyclic carbodiphosphorane catalyst was most effective in ketone hydrosilation at 1% when compared to alternative catalyst. It was also shown to be effective at higher mole percentages. For future work for this cyclic carbodiphosphorane structure, we could develop a Hammett plot using ketone competition reactions that have been somewhat performed so far. These use equal amounts of a ketone and determine which the catalyst would rather react with. We could also expand the substrate scope to include more chemical groups. We did try this with aldehydes, which vary from ketones in that they have a hydrogen where one of the carbon substituents would be. They were all found to almost immediately decompose our catalyst, so they were ineffective. We could also perform mechanistic studies using crystallization and X-ray diffraction. This would be beneficial as it would allow us to see transition states and possibly multiple transition states if there are. I would like to say thank you to my professor, Dr. Allegra Lieberman Martin, for supporting me in this research, for giving me this opportunity, and for teaching me everything that I know. I would also like to thank my friends and family and professors for supporting me along the way. And thank you to Pentane for nothing. Most of all, though, thank you guys for listening. I really appreciate your time.
Yes. So then why did you use 5 moles and then 1 mole of your catalyst? Like what made you determine those concentrations?
5 mol% is somewhat low, but would still tell us whether or not the catalysts are effective. When we found that there were some effective at 5 mol%, we lowered it to 1. The lower you're able to go with a catalyst loading percent, while it still is effective, the better it is. You know, you save a lot of money, time, reagents.
Yes.
Is it possible to separate this catalyst from the substrate and then reuse it?
Yes, we have not tested reclaiming our catalyst yet. We do believe it somewhat reforms, though some reactions do decompose the catalyst.
Yes.
So, is it possible that the cyclic form is better than acyclic, just maybe because of the availability of that central carbon lone pair?
Yes, I believe that the cyclic form is overall better because of that added stabilization that the closed ring structure gives. The acyclic would have more steric freedom, but it reacted lower overall at lower mole percentages, indicating that it does not proceed with the reaction.
Gotcha. And then, do you mind going to the slide where you create the catalyst, like we're saying, like the decarbonation?
It's going to take a second.
That's fine, sorry. Yeah.
Yes.
And please forgive me because I'm forgetting some of my PK problems, which is wild because I'm organic chemist. But for the deprotonation,
Yes.
so after the first proton gets deprotonated,
Mhm.
I guess one, just in general, like, is it possible that the other carbon, so the other alpha carbon, the carbon on top of the phosphorus, is it
Mhm.
possible that those can get deprotonated?
It's possible that those are deprotonated, but we confirm our catalyst structure using proton NMR, so we do not believe that that is the case. Yeah, we think that we're forming on this central carbon.
Interesting. Thank you.
It's complicated. That's the form that's observed in solution, but the other ones may be acceptable. So, yeah.
Great job.
Any other questions for you? Okay, not, so I need to come up with one. Okay. What is best solvent? Okay, what is in a freeze pump thaw? Which step is your favorite?
Definitely the freeze, because I get to not play with used liquid nitrogen.
All right, please join me in thanking. And it is my pleasure to introduce Chelsea Zhao, who's in my research group as well. Chelsea has been working on a new project that she'll be talking about, having to do with ways of teaching organic chemistry. But you'll see that it's experimental lab work as well. So let me turn it over to you, Chelsea.
Hi everyone. Hi everyone, my name is Chelsea Zhao. I am another chem major and senior who also minor in nutrition. And I did my capstone research with Dr. Emma Martin. Our research focuses on the visual demonstration of substituent effects for chromium-6 alcohol oxidation. What a long title. Didn't realize. So to give a little bit background before the substituent effect. So on the right of our screen, we have a benzene ring, which is a mono-substituted, which is with a R group, where the R group could be either a carbon or hydrogen. So there could be three possible ways for a substituent to be irrelevant to the R position, which is first the ortho position right next to the R group. Second, the meta position, which is one carbon away from the R group. And thirdly, the para position, which is opposite to the R group, or two carbons away from the R group. So, and again, on the right side of the screen, we have our molecule of interest, our experimental phenylethanol, and we mainly focus on the substituent groups to be on the para and meta position. So for a substituent group, it could be either a activating group or an electron donating group, meaning that that substituent is going to donate electron density to the benzene ring from itself to the reaction site essentially, or it could be a deactivating group, also known as the electron withdrawing group, that the substituent is going to withdraw the electron density from the benzene ring to itself. So why do we care about all the different characteristics of our substituent groups? Because it's going to influence the rate of our reaction. And then kinetics is always a hot topic in chemistry, and we want to study for it. So as we can know, if it's an activating group, it's going to slow down the reaction because the electron density is put away from the reaction site. And if it's a deactivating group, it's going to pull away the electron density from the benzene ring, so it's going to slow down the reaction. So this is the general chemical equations we have for our alcohol oxidation. So if we start with a secondary alcohol, as we can see the central, where's my laser? Right here. Our central alpha carbon is connected to 4 single bond, and then after the oxidation, it is converted into connecting with 2 single bond and a double bond. And of course, our chromium-6 is reduced to a chromium-3, and the color changes from orange to blue. And here is a more detailed mechanism of our reaction. We're starting with secondary alcohol, and it's first converted into a chromate ester. And this chromate ester in an acidic environment is going to be converted into a ketone and a chromium-4, which will eventually be reduced to a chromium-3. So bringing us to the overall objectives of our experiment is that we wanted to help people to understand organic chemistry, especially the substitution effect on the alcohol oxidation. And then by doing so, we approach by two ways, which is the video demonstration, the qualitative study, and secondly, a quantitative study, which is by constructing a Hammett plot that I will get to in just a minute. So for the materials and methods section, so here are the list of our alcohols we used. So we have one sort of the parent phenylethanol where there's no substituent groups, or mainly there's just hydrogen, and 4 para-substituted and 1 meta-substituted. And for the chromic acid solution, it is made up from chromium 6 oxide solid and mixed with dilute nitric acid and dilute sulfuric acid. And of course, acetone was used as the solvent due to its good solubility with the phenyl groups. So in our reaction vials, we have 1.5 milliliter of the chromic acid mixed with 2.5 milliliter of the acetone. And then to each of the vials, except for the first control, which doesn't have any alcohol in it, we injected 100 microliters of the phenyl alcohols. So we are observing our alcohol oxidation by observing the color change of our chromium complex. And then the reason why for our video we didn't do all of the alcohols is that we don't want to make it visually cluttered. It's too many, too crowded. So the first one is the parent phenylethanol. The second one is the para-methoxy one, which is also an electron donating group. And lastly, we have a para-nitro one, which is a electron withdrawing group. So this is what the reaction looks like at 0 minute at the starting point. And then at 5 minutes, we can see that the para-methoxy one has already changed the color all the way from orange to blue. And then the parent phenylethanol as sort of like in the middle, green color. And the para-nitro one didn't change color at all. And around 9 minutes, both of our phenylethanol and the para-methoxy one has already changed its color from all the way from orange to blue. And then the para-nitro still didn't have that many of color change. And then moving on to the 30-minute time zone, the para-nitro one finally started to exhibiting a greenish yellow. And lastly, at 15 minutes, all of our alcohols changes from orange to blue. So in conclusion to our video demonstration part, we can see that the para-methoxy alcohol takes the shortest time for it to complete its alcohol oxidation. And in contrast, the para-nitro one takes the longest time to complete its alcohol oxidation. So moving on to the quantitative study, which is the study of the first order kinetics of our experiment. We ran our alcohol oxidation in kinetics instrument called the Carry UV Wing, and we gathered the absorbance of our product form, which is the chromium 3 at wavelengths of 574.9 nanometer. And then after the data analysis, we take the natural log of our absorbance plotted on the vertical axis and the time on the horizontal axis, in which we can find our rate constant to be the slope of our straight line. And then here is just an example of our para-methyl alcohol with a pretty decent R-square value. Yay. So for each of our alcohol, we ran 3 or more replicates to get a more consistent value. And then here is the chart of all of the rate constant of our experimental alcohol. So as we can notice that the para-methoxy one has the largest rate constant, indicating that is the fastest among all of the alcohol in respect to the mechanism, the rate. And then on the other hand, the rate constant for our para-nitro one is the smallest, indicating it is the slowest alcohol in respect to the mechanism and the rate, which also agrees with our finding in the video that the para-methoxy only takes about 5 minutes to complete its oxidation, and the para-nitro takes about like 50, which is 10 times more the time of the para-methoxy. So yeah, so far so good. Lastly, I want to introduce the concept of Hammett plot. So a little bit of background. So in 1937, Dr. Louis Hammett, who is a great physical chemist, he was studying the substituent effect on the acidity of benzoic acid. And he introduced this concept of Hammett plot, which is the study of the electronic changes induced by the substituent effect on the benzoic acid mechanism. So he also brought up this substituent parameter sigma, which is a scale that measures the ability of substituents to influence the acidity of benzoic acid. And then on the right, we have the chart of the sigma values of all of our substituents involved in the experiment. So when sigma is smaller than 0, meaning that that substituent group is a electron donating group, meaning it's gonna increase the rate of reaction. And on the other hand, if sigma is greater than 0, it means that group is electron withdrawing group. And we can check our chart that the para-methoxy, as we already know, the electron donating group, it has indeed a negative sigma value. And in contrast, the para-nitro one has a sigma value that's greater than 0, indicating it's an electron withdrawing group. And lastly, this is the math equation that Dr. Hammett uses to derive the sigma values, in which he takes the log of the ratio of rate constant, where the numerator is the rate constant of the substituent, and then the denominator is the rate constant for the no substituent benzoic acid, in which hydrogen was used as the reference substituent. And because in organic chemistry, we always wanted to explore and investigate all kinds of unknown reaction. So in our case, we wanted to study the substituent effect on the rate of alcohol oxidation. So we introduced this Hammett plot reaction constant parameter rho, which measures the sensitivity of any new reaction, in our case, the alcohol oxidation, to the substituent effect irrelevant to the substituent effect on benzoic acid. So we adapt the same math equation that take the log of the rate constant ratio, and this time the result equals to the rho sensitivity parameter times the sigma value, which is the substituent parameter from the tables in last slide. And lastly, this is our experimental Hammett plot. And we can see that the rho value is essentially the slope of our straight line here, negative 0.51-ish. And surprisingly, we can see that if rho is smaller than 0, indicating that the reaction is creating positive charge. A surprising finding. And yet again, we have the para-methoxy one on the top, indicating it is the fastest among all of the alcohols, and the para-nitro one is the slowest among all of the alcohols. So yeah, so far so good. So in conclusion, because substituent effect is a hard concept in organic chemistry, that's why we approach both a qualitative and a quantitative study to help people to understand this concept, that the effect of substituent groups on the oxidation rate of secondary alcohol. So at the end, I would like to thank you, Dr. Lehman-Martin, for giving me this precious opportunity to be in your research lab, and for your significant contribution to this experiment, and for your all the time, your help and your care, your love. Always. Yes.
You talked about the inductive effects of some of your substituents.
Yes.
I didn't notice, did you use a chloroalcohol at all?
Great question. We tried to use the chloral. However, the observance, that graph, let me go back. So, as I mentioned, this R square is pretty decent, pretty nice, but the chloral one has like too many jumps and like this, so it's not ideal. So we just exclude it from our results section. So yeah, great question. We did care about chloral, but that's not our fault. Yeah. Sadly. So, yeah.
Dr. Andra? I'll go get your, yeah.
Great talk. I'm actually interested in sort of what you're going to do with this. So you're making a video demonstration
Yes.
with the sort of the relative rates. So is the plan to visualize both the qualitative and the quantitative changes? Like, how's that going to kind of come together? And I assume it's going to be a video. Yeah, just interested in that process, if you've thought through it.
Yeah, sure. Because yeah, it is. We have two approaches. So the video part is just to help people to like visualize like which alcohol is the fastest and which alcohol is the slowest. And then we are gonna use like math actual numbers for the rate constant, which indeed is the Hammond-Plot part, to like sort of like agree with both findings.
I see, so that would also be integrated somehow in the visualization process. Cool, yeah, that's great. Thanks.
Yes.
So,
Sorry.
this may be probably beyond the scope of what you've been doing, but I'm interested in the mechanism of the reaction, and I have to admit, I won't tell you how many years it's been since I've thought about the mechanism of chromium 6 oxidation, but do you know, well, two questions really. Do you know if this proceeds by 1 electron steps or an initial 2 electron step followed by a 1 electron step? And because you mentioned you point out a chromium 4 intermediate there.
Yes.
And does your work with the effect of substituents on the benzene ring provide any inference to the overall mechanism, the series of reaction steps that are taken from reactants to final products?
So from what I recall, so this is just like a abbreviated version of the mechanism just for the slide, the presentation. So we have a more in detailed mechanism in the iPad. So I am pretty sure the substituent group is like not necessarily involved in the actual curved arrow pushing. So basically it's just like a bunch of lone pairs from the acidic environment, on the oxygen, and then it's just like with the CO bond and the chromium oxygen bond. I think. Yeah, like 1 electron kind of.
So it's a sequence of 1 electron oxidation steps down to chromium 3.
Yeah.
And if you do this, you mentioned something about sulfuric acid and nitric acid.
Or to make the chromic acid solution, yes.
Okay. Do you find evidence that sulfate ion is bound to the chromium 3 ion if you use sulfuric acid in the preparation versus nitric acid?
Not necessarily. I believe it's just for, I believe like in the end, what's actually involved in the mechanism is just the H3O plus, essentially. Not involved in the chromium, I think. Sorry, I wish I could give a
No, it's okay,
more
it's
depth
okay.
answer, but yeah, our reaction mainly focus on the rate part. Sorry.
Yeah, we've used like an already developed method to generate chromic acid. So we haven't varied the acids at all.
Yeah, okay.
Was there one hand up over here? All right,
Then I will have one final question for Chelsea.
Sure.
Let me have some fun. Okay.
Yeah.
What is your secret to avoiding bubbles in the UV vis bed?
That is my secret to so as I mentioned, like while I was collecting the observance of my chromium 3 product, like I have to shake my cuvette really well to like let my chromic acid and alcohol to reach that perfect mix. And then since that's gonna create a lot of bubbles, I have to lift my cap of the cuvette and then let it breathe, let it breathe. So and then I put it back in and then insert in my little instrument to get the absorption. So yeah, it was kind of toxic, but that way I can get a good graph like this perfect aspect. Yes.
All right, so let it breathe. I didn't know that stuff. So please join me. Oh, did you have your hand up?
Well, it's kind of an odd question, but I see you also have a love for chemistry and tattoos. Is there a tattoo that, in terms of equations that have loved so much that you had to?
Well, yeah, hopefully. Well, so far, because as I already listed here, we have all of my alcohols that's only used in 6 ramen, and then there's a bunch more that I all love. All of these are my babies, so I cannot fit in my whole one bar. Probably, yeah. Maybe we'll just wait another
Your arms
year.
available?
Yeah, maybe wait another year to figure out my.
Next year when you present, we'll look for that.
Yeah, all right. Thank you for that.
Well, we'll have to keep an eye out.
Yes.
So please join me in thanking Chelsea one more time.
Welcome back everyone to this series, this conference, if you will. I hope you all have enjoyed your time so far in the early talks, and hopefully you're in for even more exciting talks as well today. So our first speaker is Morgan Grimes, who is a student, has been working with me in my lab, and she has been looking at the mechanism and selectivity of zinc-sulfur complexes. And if you were here for the earlier session, you might realize there's another zinc again in this particular. So we're a zinc crew, but Morgan, go ahead and take it away.
Thank you so much for that introduction. As he said, my name is Morgan Grimes, and I'll be presenting on the origins of oxidant sensing selectivity of zinc-sulfur complexes implicated in bacterial redox signaling. So when a host, such as a human, gets an injury, this leads to inflammation at the site of that injury, which activates an immune response. This immune response is typically in the form of activated neutrophils, which turn molecular oxygen to superoxide, which then gets released, turned into a hydrogen peroxide, and finally, hypohalous acids such as HOCl, HOBr, and HOSCN. These hypohalous acids can act as potent bactericides, and so, in response, bacteria have evolved to selectively sense and respond to these oxidants. They do so by using a chemoreceptor protein and an HOX sensor, which is a zinc-sulfur complex. The interaction between these hypohalous acids and the zinc-sulfur complex typically goes through a rapid OH transfer, leading to a halogen sulfenic acid exchange. This triggers local unfolding of the protein, which in turn begins that bacterial redox signaling pathway. This typically ends in a chemotaxis response, where the bacteria either move towards or away from the high concentration of hypohalous acids. So in a study done by Bastian et al., bacteria were subjected to varying concentrations of these oxidants, HOCl, HOBr, and HOCN. And by measuring the population density, which is the graph or the visual down below, it was noticed that HOCl and HOBr interact almost interchangeably. However, there's a notable difference with HOSCN, specifically that the bacteria had a higher survivability at higher concentrations of HOSCN before finally dropping off at about 400. So this begs the question, what is the mechanistic pathway of bacterial redox sensing, and why does it differ for HOSCN? So in a study done by Dr. Agba, he computationally explored the pathway of HOCl with these zinc-sulfur complexes. And in this study, he found that there were two transfer pathways. There's first a halogen transfer pathway, which goes through a sulfonyl chloride intermediate, and then the formation of a sulfonic acid. And there's also an OH transfer, which is more rapid and goes through forming a sulfonic acid. It was found in this research that the halogen transfer is the less thermodynamically favored pathway, and therefore my presentation today will focus on the OH transfer pathways. So getting into my research, I focused on the HOSCN reaction with these zinc-sulfur complexes, and I also compared all three pathways, so HOCl, HOBr, and HOSCN. So for my computational methodology, I started with a literature review. I then used that literature to predict the mechanism by which I thought my reaction would proceed. I then built the molecules in Maestro and subjected them to molecular mechanics calculations. I then did quantum mechanical calculations on them, and finally built a reaction coordinate diagram. These reaction coordinate diagrams are extremely helpful. They display the energetic data of the molecules that we're studying, and they allow us to not only analyze single pathways, but also compare multiple pathways. So we'll start with the reaction coordinate diagram. So for the HOCl system, we start with the two reactants at 0.0 kilocalories per mole. We then have an association between those two reactants at negative 3.3 kilocalories per mole, a transition state at 11.5 kilocalories per mole, the formation of the sulfenic acid at negative 42.9 kilocalories per mole, and the release of that sulfenic acid at negative 47.4 kilocalories per mole. For the HOBr system, we found that that first association was again at negative 3.3 kilocalories per mole, with a transition state at 15.3 kilocalories per mole, the formation of the sulfenic acid at negative 31.7 kilocalories per mole, and the release of it at negative 39.3 kilocalories per mole. Finally, for the HOSCN system, we have the association at negative 8.3 kilocalories per mole, a transition state at only 1 kilocalorie per mole, sulfenic acid formation at negative 6.9 kilocalories per mole, and the release of the sulfenic acid at negative 24.8 kilocalories per mole. So there are a couple of things that are notable about these reaction coordinate diagrams. The first being that the HOSCN pathway is actually endergonic, meaning that the ground state directly after, so complex 3, the transition state, is higher in energy than the ground state preceding the transition state, so complex 1. Secondly, HOCl and HOBr, both of their pathways are very energetically similar. And the third is that HOCl and HOBr proceed through a slower first step of the reaction, but a faster second step of the reaction. And that's mostly what I'll be probing in my research. So we'll start with that transition state barrier that we found. So for HOBr, the transition state barrier was 18.6 kilocalories per mole, and it was the highest transition state barrier. For HOCl, it was 14.8 kilocalories per mole. And for HOSCN, it was the smallest at 9.3 kilocalories per mole. So the biggest question here is why? Why does this reaction proceed the fastest with HOSCN? And what differences can we find? So to answer that question, we use two different techniques. We use charge analysis and distortion interaction analysis. So charge analysis looks at the charge of the atoms and how they shift from complex to complex. Distortion interaction analysis looks at how geometrically distorted the molecules become, and then the interaction between those molecules that overcomes the distortion. So we'll start with the charge analysis. So for the HOBr and HOCl cases, we saw that the halogens, so bromine and chlorine, started with a slightly positive charge, but moving to complex 2, they both shifted to a slightly negative charge. However, with the HOSCN case, we found that both the sulfur and the nitrogen appeared to have little change from complex 1 to complex 2. This could be indicative of us finding an early transition state, meaning that the transition state geometrically and charge-wise is more similar to complex 1 than it is to complex 3. So we'll move on to distortion interaction analysis, and we'll start with the HOSCN case. So there are a couple things to note here. The first is that the red and blue arrows are the distortion of the molecules. That blue arrow is the distortion in the hypohalous acid, so HOSCN, and the red arrow is the distortion of the zinc complex. The green arrow that you're seeing is the interaction of those two molecules, and those two added together give you the black arrow, which is the activation energy. So for the HOSCN case, we're seeing minimal distortion and a significant amount of interaction between those molecules. And this is reflected in the transition state barrier. So it's the lowest transition state barrier. This is also confirmed geometrically. As you can see, the bonds are not changing from complex 1 to complex 2. Next, we'll move to the HOCl case. We see significantly more distortion of the molecules, but still we see interaction that's overcoming that distortion. And this geometric distortion is coming from the elongation of the bonds in both HOCl and the zinc complex. Finally, in the HOBr case, we're again seeing even more distortion, and the interaction is actually not overcoming fully that distortion. And we're seeing, again, the elongation of those bonds, both in HOBr and the zinc complex. So this is kind of confirming with the geometries that we did indeed find an early transition state. For HOSCN, the transition state, complex 2, looks extraordinarily similar to complex 1, which is accounting for this low transition state barrier that we're seeing. So next, we're going to look at the sulfenic acid formation and a hypothesis for the protein unraveling. So the sulfenic acid formation is integral to the protein unraveling, as the sulfenic acid release is what starts that process. So for the HOBR and HOCl cases, this is an energetically favored pathway. So we're seeing that complex 3 is dropping in energy. For HOBR, it's negative 28.4 kilocalories per mole, and for HOCl, it is negative 17.8 kilocalories per mole. However, with the HOSCN case, we're seeing that there's actually an increase in energy there. So complex 3 is higher in energy than complex 1. This is implying that the equilibrium of this reaction is lying closer to complex 1 than it is to complex 3, meaning that HOSCN may not start this process and may not go through protein unraveling. This is actually confirmed by the study of Bastian et al., in which they looked at unmutated wild-type bacteria, and they found that HOSCN did not cause protein unraveling and did not activate the HSP33 signaling pathway. So, conclusions and future research. The HOSCN pathway differed greatly from HOCl and HOBR. It's actually endergonic, meaning that it is unlikely to cause that protein unraveling. And it possibly has a unique mechanism for being a bactericide. Also, in the study by Dr. Agba, the HSCl pathway was fully computed, and there was an additional transition state for the OH transfer pathway between complex 3 and complex 4. So additional research will need to be done to find that transition state for the HOBR and HRCN cases, and that should give us a better overview to fully compare these pathways. In addition, the SCN pathway, we started research on that pathway, but we have not fully computed it, so additional research will be needed there. And I'll leave you with a few remaining questions. So if HOSCN does not cause protein unraveling through the HOX sensor, is there a separate target within the bacteria that allows HOSCN to act as a bactericide? And also, why is the energetic data of the reaction so similar reaction so different from HSCl and HOBR when the geometric pathway for all three are very similar? And additional research will be needed to answer these questions. So I'd like to thank my principal investigator, Dr. Agba, for being an excellent mentor and for this research, and also my lab members for always supporting me. And then I have some acknowledgements: the Center for Undergraduate Excellence, James Kelly, who's the Senior Systems Administrator for the KET cluster, the Office of Research, and also ISMT. Thank you so much.
Thank you. Okay, questions for Morgan.
Just one question for your transition, activation of the diagram. Why do you have double delta G?
Yes, that is a good question. So on that, so the way that the energies are computed, they're all relative energies. So we're looking at the energies in comparison to the two reactants, which we have put at 0, 0. So all of those values are actually already delta Gs. So when you then subtract them again, they are delta Gs.
Thank you.
What was your most unexpected result during this research?
I think for me, it was probably the geometric similarities with the energetic differences. I thought that was very interesting because it seemed like the complexes kind of formed the same way, but HOSCN was clearly interacting very differently. We also found that in the final complex, so complex 4, instead of the sulfur attaching to the zinc, we found the nitrogen to attach to the zinc. So that was really interesting.
Great job, Morgan. Are there studies showing the similarity of pattern that you've discovered here experimentally?
Yes and no. So there is a study that I referenced, this one, which does, they did subject the bacteria to these specific hyperhalous acids. However, there's a little bit of a disconnect because a lot of times with the biological studies, it's more of like population density than it is like mechanism. So there's kind of a little bit of a gap. They have seen that all three act as bactericides. They've seen that there's a difference in HOSCN, but that difference has not been experimentally probed.
Well done.
What was the most challenging part of this research?
That is a very easy question. So we were trying to also compute the SCN pathway, and we found that the nitrogen is just extremely reactive. So trying to find the transition state, I've probably run like 15 different scans and a million different like geometries trying to find that. So that was probably the hardest part.
Any more questions for Morgan? So in the spirit of the earlier session, I didn't realize that I had to come up with other questions.
You don't have to.
No, I will. So I have a question for you, and only the folks in the lab will probably get it, but Excel or numbers for spreadsheets?
Oh my goodness. Oh, that's a tough one. I think for the research we were conducting in the lab, I would have to say numbers. I do like numbers better, but Excel has more functionality in my opinion.
Diplomatic answer. I appreciate that. That's good. And thank Morgan. Okay, well, welcome back again. It is my pleasure to introduce Gabriela Nerhood, who is also in my lab. And once again, I love the themes for this today. If you've been staying on here in this room, you've probably seen that one carbon diphosphoranes in the earlier session. And so Gabby will be studying or talking about her work, looking at the mechanistic insights into the use of these carbon diphosphoranes as catalysts. And this is in collaboration with the Sullivan Martin lab. So, yeah, there you go. Take it away.
Thank you, Dr. Osma. Yeah, I'm Gabby, and I'm going to be presenting you guys my research on the mechanistic insights into the use of carbodiphosphorane ligands as Lewis-based catalysts. So to begin, why should we study organic catalysis? Well, first of all, about 20%, the American Chemical Society estimates that about 20% of the United States GDP is in catalysis and catalysis reactions, which is a lot of money, and therefore we should care about it. But for organic catalysis, particularly, as you guys have probably heard from the previous organic presentations, the standard right now is transition metal catalysts, which are expensive, rare, and very toxic. Here are a few common ones, and their price per kilogram: rhodium, palladium, and gold, really expensive. And then as compared to organic elements that will be in my specific catalyst, carbon is about 12 cents per kilogram, and phosphorus is almost $3 per kilogram. So much more cost effective. And with that being involved in the GDP, like we want to make sure we're doing cost effective things in regards to catalysis. So when it comes to organic catalysis, there are a few different ways we can catalyze reactions. I'm going to be focusing on Lewis-based catalysis. So yeah, what makes for a good Lewis-based catalyst? Well, a good Lewis-based catalyst needs to have a Lewis-based electron donor and a Lewis acid electron acceptor. So this interaction creates a charged or partially charged adduct, which will drive the reaction forward. So in this way, a good Lewis base donor is one with a high electron density that is readily available to donate its electrons to the Lewis acid. Another aspect of catalysis that is really important is that we have thermodynamically favorable steps, so that we have delta G's that are negative for the most part. But most importantly, we want the last step to be negative for sure, because this is our turnover step, where we're going to be regenerating the catalyst. The regenerative nature of catalysis is what makes it so cost effective. We can do a lot with just a little bit of catalyst because we're constantly reforming it and reusing it. So there are a lot of different Lewis-based catalysts, but I'm going to be focusing on carbodiphosphoranes, or CDPs for short. These are carbon zero compounds that are highly unique and reactive due to their unique electronic properties and geometries. They may exist in any of these three resonance forms: the allene, the ylide, or the double ylide, and that will dictate how they react in reactions. Previously, they have been used as strongly donating complexes in organometallic complexes. They have strong sigma donor properties and high electron density, making them valuable for this. This is a crystal structure from some work done by Rhett Samer and their team, which is has a carbodiphosphorane complex with an iridium. So in this way, based on what I've said about Lewis-based catalysts, this would suggest that they would be good Lewis-based catalysts since they are good at electron donation in organometallic complexes. So that's kind of the motivation for using them in Lewis-based catalysis. Okay, so this is the catalytic system I'll be studying. It's a hydroboration reaction involving a carbodiimide and a pinnacle borane. Dr. Lieberman-Martin's lab has done some experimental work on this specific system, looking at carbodiphosphoranes as compared to other Lewis-based catalysts and showing their high effectiveness. So here are the conversion rates for the carbodiphosphoranes in 5 hours. The cyclic version has 99% conversion, and the acyclic version has 82% conversion, which is really good. Then looking at the oxygen Lewis-based catalysts, in 24 hours, the highest that we see is 17%, which is not great. And then other common Lewis-based catalysts, again, the highest that we see in 24 hours is 17%. So time and time again, the carbodiphosphoranes are doing a lot better job at catalyzing this specific reaction. And specifically, I want to point out here that there is a like single illid version of the carbodiphosphorane here on the right, and it has 0% conversion in 24 hours, which would suggest that the double illidic character of carbodiphosphoranes is at play somehow in making this making them a good catalyst in this reaction. So yeah. Here's my general methodology. I began with a literature review. Then, using chemical intuition as well as the literature review, I guessed the mechanism for this reaction. I then performed conformational analysis in molecular mechanics using the OPLS 2005 force field. And then I brought these structures to higher level quantum mechanical calculations to refine the geometries, get more accurate electronic energies, as well as accurate atomic charges. And then lastly, I did some spreadsheet analysis to generate a reaction coordinate diagram using the associated energies from the quantum mechanical calculations. All right, so this whole research is really asking, what is the mechanism of this reaction in the presence of carbodiphosphoranes? So nothing is really known about this mechanism, and specifically the mode of activation is unknown. So there are two plausible modes of activation, which will lead to two plausible catalytic cycles. So the first would be a nucleophilic attack of the boron in the pinnacle borane, forming this adduct. And then the second one would be a nucleophilic attack of the central carbon on the carbodiimide, forming this adduct. Depending on which molecule the carbodiphosphorane nucleophilically attacks first will determine the full mechanism. So I'm going to go through the full mechanisms for both of these options. So I'll start with the carbodiimide first side. Oh God, PowerPoint, I hate you. Okay, so we start with the adduct formation step. Like I mentioned before, there's a nucleophilic attack of the carbodiphosphorane creating this adduct. Then we have the boron-nitrogen bond formation, where the nitrogen will attack the boron and make this complex. And then lastly, we have the product breaking off and reforming of the carbodiphosphorane. All right, now to the borane first side, we have the adduct formation, again, the nucleophilic attack of the boron. And then we go to the hydroboration step, which we will have a hydride transfer to the carbon and then the boron-nitrogen bond forming here too. And then we'll have the product formation step where we'll reform the carbodiphosphorane and break off the product. So I'm going to be focusing mainly on the borane first mechanism because I read a paper by Zhang, and they were studying a catalytic hydroboration as well with a similar mechanism, and they deduced a borane first mechanism. So that's the one I'm going to start by studying, but research will have to be done on both sides to compare them thermodynamically. All right, so the first step of my research involved looking at the carbodiphosphorane as compared to the single illid version, and looking at the first step of the borane first side, looking at the thermodynamics, the Gibbs free energy, and the enthalpy, as well as the charge on the hydride on the adduct, because that will help drive the reaction forward. So here were the results for the carbodiphosphorane and the results for the single illid. So as you can see, the delta G and the delta H are lower on the carbodiphosphorane than the illid, which confirms the thermodynamic preference of carbodiphosphoranes in this catalysis reaction. And the charge on the hydride was lower in the carbodiphosphorane, but I was looking at some of the literature and specifically this paper by Zhao, and this hydride difference is not significant enough to like make a valid claim that that's contributing to the success of carbodiphosphorines. So I'm not really going to focus on that, more about the thermodynamics, because that seems to be the bigger difference between them. All right, so here's my reaction coordinate diagram. So the first step is the adduct formation step, which goes down in Gibbs free energy. And then the carbodiimide coordination step, which goes slightly up. Then we have the hydride transfer transition state, which goes up to 16.3 kilocalories per mole, giving the reaction barrier a barrier of 21.9 kilocalories per mole. And then after the transition state, we go down steeply down the hill to negative 31.7. For the BN bond formation, we go down again. And then lastly, the product release step goes down to negative 36.5 kilocalories per mole, which is good because this is our turnover step, and this is the one we really want to be negative so that we can reform the catalyst, like I mentioned earlier. All right, so I'm going to focus now a little bit on my transition state that I found. This was the transition state which I saw, but it wasn't exactly the transition state I was expecting to see. So in this one, we just see the hydride, the hydrogen transferring between the carbodiimide and the boron, and it's kind of just going back and forth. And what I expected to see was that hydride transfer, but as well as the boron nitrogen bond formation, which I didn't see. So this is suggesting to me that this could be a stepwise mechanism. To confirm this, I ran an IRC scan, which basically we start at the top of the hill at the transition state and we scan down to find the connecting ground states. And those ground state geometries will tell us whether this is concerted or stepwise. If we have a concerted mechanism, this is what the product ground state will look like, on the right. We'll see the boron nitrogen bond forming and the hydrogen on the carbon. If we have a stepwise mechanism, the IRC will show us a formation like this, where we just see the hydrogen going to the carbon, and we haven't yet seen the boron nitrogen bond forming yet, and that would happen in a next step. So based on those results from the IRC, I confirmed that this was actually a stepwise transition state, which is really interesting. After the IRC, this was the product that was seen on the the product side, which confirmed the stepwise mechanism. I also have included the bond length of 3.5 between the boron and the nitrogen, which is they're not close enough to be a boron nitrogen bond. So yeah, that was really fun. And for my conclusion, so I've completely done the borane first catalytic cycle, looked at the thermodynamics of it. So yay, but we need to still do future work on the carbodiimide first mechanism in order to confirm which is the more thermodynamically favorable and thus more likely path. So yeah, and I want to thank my whole lab group, Dr. Ogba, for giving me this amazing opportunity. And I want to thank the CUE, Schmid, the ISNT, and James Kelly, who is the Senior Systems Administrator for our cluster. Yeah, thank you.
Okay, questions? Oh,
Are you a numbers or Excel?
I'm a numbers. I like numbers. Yeah.
Okay.
It just like looks better.
It's a good bar.
So Gabby, you mentioned there's these two possible mechanisms that you're looking at. What do you think might differ between the data that you would get to indicate which of those two mechanisms would be the more likely mechanism?
Well, I'm still of the belief that the borane first mechanism is the one that's happening, just because, well, I also have like emotional attachment to it, but but the difference would be like that we would see like differing delta G values for those steps. And a lot of if you go back to my reaction coordinate diagram, most of my steps are going down in delta G aside from that 1 to 2 step. So I would just expect that for the carbodiamide first side, we would see it wouldn't be as thermodynamically favorable as this side, if that answered your question.
It's a real question, I promise. So kind of moving on to your like future study, do you anticipate the methodology and kind of like how you've conducted all your tests and stuff to be similar, or do you expect to potentially try a different method to get to the conclusion really?
Yeah, I think it would be for the most part similar, using the same methodology just so that we could compare these two accurately, because if we kind of just started to change the methodology, they might not be as reliable of results to compare the two. So yeah, I would anticipate that it'd be pretty much the same.
So how was, I guess, the first steps of this project? Understandably, I know you started about a year ago, and this computational chemistry seems to have a very large learning curve. So yeah, how did you get started?
Yeah, I would definitely say like the learning curve was the hardest part. I like didn't really even know what computational chemistry was until I joined Dr. Agba's lab, and I only did it because Zach was like talking how awesome of a mentor Dr. Agba is, which he is. But I definitely, that first summer, I was just reading and like, I'm not getting this, like the papers. But honestly, like once I read like all the papers and went over them with Dr. Agba, it was really crazy how like the vocabulary just started to come up and I just started to understand it. So definitely a really steep learning curve, but it's really nice now. I feel like I can really see my progress, which is fun.
Great job, Gabby.
Thank you.
I'm intrigued about the turnover step there and how that the experimental work that's already been done and this turnover step, how do they compare?
Well, I haven't looked like into the experimental work exactly like that closely, but we did see that the carbodiphosphoranes were experimentally really successful, which does align with this showing the negative turnover step. But like specifically in like the experiment, I'm not exactly like sure because we still aren't even entirely sure on the mechanism, but from this information, it seems to like align with it pretty well.
So it aligns that it is catalytic.
Yeah.
Gabby,
hi.
I'm curious. So the hydride transfers first, which is really interesting.
Yeah.
And then, so after the hydride transfers, the way you've drawn it on this slide, it looks like the hydrogen is sort of still interacting with the boron, right? Is that what it looks like?
Yeah, I might have just drawn it like that. I don't think that they're like still really.
I think you had I think on a later slide, could you go to the slide where you have the maybe the one after this?
Yeah. Sorry, all these builds.
So it looks.
Yeah. So this is the like product side after the hydride transfer. So yeah, it looks like they're not really as interacting as I drew it on the chem draw.
Is that the nitrogen, the 3.5?
Yeah, that's the boron nitrogen bond. And I just brought that up because in the actual final step where we have the boron nitrogen bonded, there the length is about, I think, 1.4 angstroms. So I just was highlighting that that's not yet a bond between them.
That's really interesting. Yeah, the like stepwise pathway that you talk about, people see it a lot for Lewis acid catalysts.
Oh.
Because the Lewis acid would be attached to the nitrogen or something like that, so it would stabilize it. But I don't think it's as common for these bases. So this is pretty cool.
Definitely wasn't what we were expecting.
No, yeah, I mean,
yeah.
Thank you.
that kind of raises the question of all the carbon and phosphorus of the actual one there. But, yeah.
Yeah, I asked Gabby about that.
Yeah. Yeah. More questions for Gabby? I do not. Well, thank you so much. To introduce Kanesha Scott, who is also another researcher in my lab. And Kanesha has been studying for the past year or two, maybe year and a half. Year and a half. The catalytic reduction mechanisms mediated by these half sandwich complexes and cooperative catalysis. She's specifically looking at the role of the metal, the reagent, the ligand, everything in affecting the reactivity of the system. And with that, let's take it away.
Let's get started. So I'm going to start my talk today by focusing on HH bonds, which in the world of chemistry are very interesting due to the fact that they are extremely hard to break, which makes sense due to the fact that they're very stable and non-polar. If you were to wait for these two atoms to dissociate, you'd be waiting a long time, probably forever. But chemists have come to understand that in facilitating this process, it's helpful to use transition metal catalysts. And when looking at the advantages of this, you can see why. The first one being that it successfully activates HH bonds, like I just said, and it does this by lowering the energy of activation, like catalysts mostly do. So, because without the catalyst, like I said before, the reaction wouldn't occur. The second advantage being that it has many applications due to the fact that in activating HH bonds, they produce products and intermediates that can go on to be used in the drug and agricultural industries. But like any process, it has its cons. The first one being the fact that transition metal catalysts are very rare and are thus very expensive just per gram. There are some examples like on the slide. The second con being that when using these transition metal catalysts, they also require very harsh reaction conditions. So this means high temperatures, high pressures, which help contribute to the ever increasing cost of the process, as well as just bringing safety into question. The second activation process I want to focus on today is the activation of silicon hydrogen bonds. These are interesting because they are much easier to activate than silicon hydrogen bonds, but they still require the use of transition metals, which brings us to a similar set of pros. One deviation being the fact that it can serve as an alternative bond activation process to that HH activation. The only caveat here is that it requires multiple steps. But yeah, since transition metal catalysts are still being used, it still has the same amount of cons. You can see why it's favorable to produce a more milder and safer catalytic alternative, which nature happens or may offer us an alternative with that. So that leads us to my discussion on nickel iron hydrogenases, which are naturally occurring enzymes in bacteria. They have been seen to naturally activate HH bonds, which is important to the discussion here today because relative to that of transition metals, it activates HH bonds under much milder conditions. So synthetic chemists saw that and said, well, how about we try and mimic this synthetically, creating this whole basically subset of catalysts, one set of catalysts being metal nitrogen complexes, which are the most well-studied metal ligand complex. But if you look back at the nickel iron hydrogenase, it does activate at a nickel sulfur bond. So that brings us to the discussion of what exactly do we know about metal sulfur complexes? Well, they've been seen to do a lot, actually. There's been an evolution of sorts in the types of catalysts basically generated. The first one, Ratros and collaborators saw that this catalyst was successful in activating HH bonds. A few years later, Oki and Tatsumi, as well as others, found that this catalyst was successful in activating not only HH and silicon hydrogen bonds, but also boron hydrogen bonds. In 2008, Stradiotto saw that this catalyst was successful in activating silicon hydrogen bond. And in the same year, Oki and Tatsumi saw that this catalyst was successful in activating HH bonds. But looking at those last two
catalysts, a few key differences showed up that I thought was pretty interesting. The first one being that when the Stradioto and the Oki and Tatsumi catalysts were used to activate HH, no reaction was seen with the Stradioto molecule, but with the Oki and Tatsumi molecule, the reaction was successful, which suggests that the absence or the presence of a chelated ligand may change the reactivity of the catalyst. The second thing I saw was that when using the Stradioto molecule, while it wasn't successful in activating HH, it was successful in activating silicon hydrogen, which implies that maybe reagent choice changes the reactivity of the catalyst. And lastly, with the same Stradioto catalyst, they used both iridium and rhodium in the analysis process. And when iridium was used, a stoichiometric amount of the catalyst was used. Basically, it was absorbed in reaction, while when the rhodium variant was used, it was regenerated. So yes, which brings us to another paper which shows another distinction when using different metals. When using this iridium variant, the HH, the two hydrogen atoms individually bonded to the metal before one of the hydrogens transferred its bond to sulfur, reflective of a dihydride intermediate. But when the rhodium variant was seen, the HH bond bonded to rhodium through an 8-2 coordination before, again, that bond was transferred, reflective of a dihydrogen intermediate that was also seen with cobalt catalyst in another paper. So that brings me to the beginning of my project currently and the research questions that I have investigated. The first one being is what role does the metal identity play in activating hydrogen towards ketone hydrogenation? Secondly, how does that change when phenolsilane is the reagent? And lastly, how does that change when making the PS ligand chelated or non-chelated? And so to do this, I followed a general methodology with first guessing the mechanism based off my chemical intuition, as well as some of the literature sources that I've presented so far in the presentation. I then modeled that mechanism in Schrodinger Maestro before subjecting those stationary points to OPLS 2005 molecular mechanics force field before taking the geometries and energies from that and optimizing them, and then using those to do thermodynamic calculations and generate a reaction coordinate diagram for comparative analysis. So that takes me back to my first question: what role does the metal identity play in activating hydrogen towards ketone hydrogenation? And basically, to investigate this, we first started by looking at the bond activation process. And so when given the chelated catalyst, how does iridium activate hydrogen? To answer this, I first generated a transition state scan with Gaussian as the model, B3-LIP as the metal, 631 GDP and Lanol 2DZ as the basis sets. And in doing that, I basically saw that the two hydrogens bonded individually to the iridium before one of the bonds was transferred to sulfur, reminiscent, and when that transfer process occurred, the distance between the two hydrogen atoms was fixed, which is consistent of a dihydride intermediate due to that fixed distance. So overall, the reaction basically makes it to where the hydrogens individually bond to the iridium through oxidative addition, and that transfer step is reminiscent of a reductive elimination, which is exactly what was seen in the literature, except the key difference here is that in the literature, they used a non-chelated catalyst versus the chelated catalyst used in my computations. Which in comparison to the rhodium cobalt and rhodium and the cobalt variants, which some interesting things were seen with the rhodium and cobalt variants. One, they also had the same mechanism, but also when the hydrogen came in contact with the catalyst, the hydrogen bonded to the metal through an 8-2 coordination, reflective of a dihydrogen intermediate relative to iridium's dihydride. So I say this all basically to say that this is also consistent with the literature, but like as I said before, a non-chelated catalyst was used in the literature versus a chelated one in the computed calculations, which brings us to our first big conclusion that the activation mechanism does not change when changing the identity of the ligand. And one caveat here I wanted to mention is that while the rhodium and cobalt variants had the same mechanism, they did differ energetically, which with further calculations on the transfer step will provide more information on that, as well as
that being a more important part of the discussion. So that takes me again to the second question, which is how does basically the reaction change when activating phenolsilane? And again, I started with the chelated iridium variant. And in doing so, the hydrogen and the silicon group both individually bonded to the metal before the bond transferred to the sulfur, which again, the distance between the silicon and the hydrogen was fixed as this transformation occurred, which, if you remember what I mentioned earlier, these two reactions are exactly the same when activating phenolsilane and HH. So that brings us to our second conclusion, which is that activation mechanism does not change when paired with different reagents. So that takes me to my final, or my summary here, or of what I want you to take away from this presentation today. As I said before, there's been an evolution in the types of metal sulfur complexes that have been used as catalysts, and they've been seen to activate numerous amounts of bonds, different types of bonds. But the problem is that we don't know exactly why different catalysts are able to activate different bonds. For instance, why is, like I raised earlier, why is the Okitatsumi catalyst able to activate HH, but the Stradioto catalyst isn't able to activate it? Is there something going on mechanistically? These are all questions that were raised, but based on the research done and presented on today, we've come to the conclusion that ligand identity and reagent do not change in the change in mechanistic differences with regards to the bond activation process, but metal identity ultimately does. So that takes me to the end of my presentation. I want to thank the Center for Undergraduate Excellence, as well as Schmid College, as well as the Office of Research, James Kelly, and IS&T. I also want to thank the OMO Lab group for their support here today and other times as well. And I also want to thank Dr. Agua for his encouragement and guidance throughout this project. So thank you. If you have any questions.
Okay, questions for Kanisha? Yes.
What was one specific unexpectedly interesting result that you had?
I think basically this reaction mechanism, this took a really long time to compute, and I just thought due to the difference of reagent and the fact that it's a much more bulky reagent, I didn't think it was going to have the same mechanism, but the fact that it does was kind of surprising. So.
Well, I have a question for you. And this question is more of a brag on you because as I know, you have been accepted to several PhD programs in chemistry, which is great. So Kanisha's going off at Texas A&M. So my question for you is, what are you most excited about going into graduate school in the fall?
I guess sort of seeing like the whole scope of the process. In the lab that I'm in right now, I'm primarily focused on computations, and we don't really do anything experimental, but I know like in a lot of different research groups, they kind of do a combination of the two. So basically seeing that interaction, I'm kind of excited to see. So.
Great, wonderful. Well, let's go ahead and thank Kanisha. It is my pleasure to introduce Vanna, who, and this is also a little bit of a change in the presentations. We're now up to food chemistry today. And Vanna has been investigating honey fraud and by some spectroscopic techniques, HNMR, as well as moisture percentage. And yeah, followed this work for a while. I'm excited to see where Vanna has taken this to. So welcome, Vanna.
Alrighty, hi everyone, my name is Vanna. I am a chemistry major, nutrition minor, and I will be presenting my project on the investigation of honey fraud by proton NMR and moisture percentage. So a little introduction. So honey is a natural sweet substance produced by bees from nectar extracted from flowering plants or excretions of plant-sucking insects living on living parts of plants. Clover honey is a monoflora honey made with nectar of at least 50% clover flowers. And wildflower honey is a polyfloral honey made from nectar from various wildflowers, including clovers. So I came up with the idea with this project because I was in OChem, doing my usual literature search in lab. And I found that proton NMR was a recent effective method in detecting honey fraud, and I thought that was really interesting. So I wanted to come up with a project for myself. So honey is a major food target for adulteration, ranking just under milk and olive oil. And it can be adulterated by different ways, such as blending or diluting with cheaper sugar syrups, such as corn, cane, beet, rice, wheat, or tapioca. It can also be diluted with water, and this can occur from an early harvest, and it creates an ion exchange resin process, which lessens the color and flavor of the honey. It can also be substituted with less expensive honey, which is seen from certain Manuka cases, if certain people are following with that. And anything over 18.6% of a moisture percentage is considered diluted for grade A and B honey, according to the USDA. And previous methods for detecting honey fraud include carbon-13 NMR, but this is only for sugarcane and corn syrup, and it doesn't account for other sugar syrups such as rice, beet, wheat, and tapioca. So that's where my project comes in. So the objective of this project is to analyze the quality and authenticity of the honeys being sold on the US commercial markets. I will be giving a brief overview of my research process in this past year. So what I first did was I collected 30 honey samples, focusing mainly on clover and wildflower. And then I went into honey moisture data collection and analysis, which I will go into more detail later, as well as proton NMR data collection analysis. And right now I'm currently in preparation of my manuscript, which I will be submitting this summer for publication. So going more into detail of the methods, I collected 30 honey samples from an online retailer and from 5 commercial markets in the Orange County region. I won't disclose the name of these markets because, as you can understand why. And I focused on clover and wildflower honeys based on the lack of research when I was doing my literature search. And I collected corn syrup, beet syrup, rice syrup, glucose, and fructose, and collected that as a reference when collecting my NMR data. So for honey moisture percentage, I used an instrument called a digital refractometer to measure, and so I used that, and it measures in Brix values, which mainly, I describe it as the amount of sugar in an aqueous solution. So essentially, the higher the Brix value, the more sugar in the solution. So of course, we can't really measure honey moisture percentage off that. So I converted that using a conversion chart from the Canadian Food Inspection Agency and made an equation, which is, for some reason this corner, right there. And so what I did was I got the Brix value, input it into the X, Y value, honey moisture percentage. And any crystallized honey, I homogenized it by stirring it at a low heat. And then I strained it using a stainless steel sieve with a 0.5 millimeter diameter, just to remove any extraneous matter from the honey. And then I measured each sample 7 times and calculated the average. So going into the methods for proton NMR, I adopted this procedure from Dr. Mark Spiteri from 2015. In my lock solution, I used deuterium oxide solvent, and my internal standard was trimethylsilopropionate. In my buffer solution, I inputted potassium phosphate, water, and sodium azyme just to protect the solution for a long period of time, since I've been working on this for about a year now. And I adjusted the pH of this buffer solution to 3.10 every time I collected an NMR data, just to make sure that I also was in contact with one of the authors from the paper, and he suggested that I go to 3.10 for a pH because it increased the organic acid region of my NMR spectra. And I also used a water suppression technique to decrease the water and deuterium oxide peak in order to intensify the other peaks. I will go into more detail of that later. And then I tested each sample in a duplicate. So some challenges faced when going through this project. The water suppression technique was a great one, but it also really helped me improve my project in general. So this is before I applied the water suppression technique. This is the water and deuterium oxide peak around 4.7, 4.8. And as you can see, it is very, very large and makes my other peaks very, very small and hard to analyze. So what I did was, after I applied the water suppression technique, which is basically changing the parameters in the NMR instrument, I found my spectra like this. So clearly you can see the water suppression made the water peak a lot smaller and still visible, while making the other peaks a lot more easy to read and analyze. Another problem that I ran into was this weird shimming and tuning issue that I'm still trying to figure out why it's happening. But basically, this weird ugly lump right here makes it very, very hard to analyze my peaks because, you know, it's right there and not doing me any good. And how I've been trying to fix this is I would rerun the sample multiple times, and I found that it decreased the lump, but not completely. So I'm still in the process of that and how to make it more clean. And as every researcher deals with at some point in their life, I also dealt with supply chain issues and shipping delays, which, you know, delayed my progress in the project because I'm currently still waiting on some NMR tubes so I can collect the rest of my data. But as we move on to results, these are my honey moisture percentages. So the ones in light blue are what I measured to be under 18.6%. And as I mentioned earlier, 18.6% and below is the required for USDA. So, and I also calculated the standard deviation, and that was also under 18.6%. So I'm confident in saying that these honeys in blue are at the required moisture percentage. The ones in purple, they were also measured under 18.6%, but when I calculated the standard deviation, it was found above the standard deviation bar, so above 18.6%. So it is possible that these honeys may be diluted, but I will need to do further research. And in a similar case with the green, which is only about 3, these were measured above 18.6%, but the standard deviation made it below 18.6%. So it is possible that they may not be actually at a moisture percentage above 18.6%, but like I said before, I will need to do some more trial runs. And then in the red is where I calculated that it was above 18.6%, as well as the standard deviation above 18.6%. So I can confidently say, well, it's most likely that these 4 samples were diluted, but you know, I can't say anything yet. And for honey sample number 13, I found the highest moisture percentage, which was around 20.38. And I think that's all I want to talk about. So this is my spectra for the proton NMR. In the first line, as you can see, is my real honey that I collected from Dr. Hellberg. Thank you, Dr. Hellberg. And this is a blended honey syrup that has corn syrup in it. And the reason why I know that is because it listed in nutrition facts. So I was like, that's a cool thing. I can add that in there as a comparison. And then on the bottom right too, I have rice syrup and corn syrup. And I also took spectra of glucose and fructose to see where I can differentiate between those peaks and possible sugar syrup peaks. And so what I found are the most differentiative peaks that I found with glucose and fructose was this triplet peak for glucose and this doublet peak for fructose. And then that whole messy area in between that are monosaccharides and disaccharides. So I would ask if you ignore that for now until I figure out how to make it look a little better. But what I really want to focus on is this far left peak right here in the corn syrup and rice syrup. So you can see in the real honey, there's no peak there, but in here you can see there is. So I concluded that that could be the biggest indicator for detecting honey fraud in honey samples. But as of the 6 samples that I've analyzed so far, there's been no clear indication of sugar syrups mixed with the honey. But I am going to, in the future, I will be doing quantitative analysis by integration and trying to find the percentage of where these, trying to find the percentage of like sugar syrups that could be in possible honey samples. And as like I said, rain samples are still being currently tested as soon as my NMR tubes get delivered. So in conclusion, proton NMR is an effective method in investigating honey fraud, and 4 out of the 30 honeys that I tested were confidently above 18.6%, indicating a possible dilution with water or other substances. And once I finish my NMR testing with the remaining samples, I will be submitting my manuscript to a scientific journal for publication. I just want to thank Schmid and Center of Undergraduate Excellence for giving me the funding for this project, as well as all these wonderful people, my friends, my family. Yeah.
Great, thanks so much for that talk. We have time for questions. Let's go. Yes, yeah.
So do you happen to know out of the 4 diluted honeys, like where are they from? Like,
I don't know if I'm allowed to disclose that yet, but if you could take a guess, there's only so many commercial markets that you would know, so.
let's start with A.
Once I get some more detail, I'm sure maybe I could disclose it. Not right now.
So you said there were issues with gathering enough proton NMR spectra. Is there something preventing you from using materials you already have on hand for that?
So one thing I found out recently when I was contacting one of the authors was that I couldn't reuse the NMR tubes that I used because the honey just makes it impossible to make it clean as before. Unlike when I worked in Dr. Lehman Martin's, I was able to clean it with acetone, and I tried that, and it didn't necessarily work. Like it did, but like and so he told me, he's like, no, you have to use a new tube every time. So I was like, okay, so I have to order new NMR tubes. But yeah, that would be, I don't know if that answered your question. Yeah.
Of the 4 that you think are polluted, is there any indication on their labeling that they contain anything other than honey?
I didn't find anything. I looked at all of the nutrition facts of the honeys, and the only one that I found was the one that I put. All right, well, the blended honey syrup, but yeah, all of them would say like just honey and ingredients.
That's a food safety issue.
I'm just curious, the samples that you collected for like the honeys, did you pick brands that like are shipped across the country or like only local ones or?
Yeah, that was a typo on my objective part. It was like I did get them shipped from it wasn't just Orange County. So it was like US commercial markets in general.
Do you think there would be a difference between ones that are like commercially made like that and like local growers or anything like that?
I do think it could be because in the commercial markets, like it's a mass production, so they probably want to come up with the most effective, cheap way in creating honeys, and it's nothing more cheap than blending it with something else. So.
Oh, well, okay. You first, and then we'll.
Was there any difference you could see in like the raw honeys? Because they're kind of, a little different.
Yeah, I couldn't really find anything because I did get both kinds and it wasn't really a difference. But yet again, I'm still in the process of collecting all of the data I only have the first like 6 right now.
So Vanna, I think this project is great. You did a wonderful job.
Thank you.
And I would ask, did you explore any other techniques to look at possible honey fraud, like UV-Vis or IR or?
It's funny that you say that because I did, and it did not go well. Yeah, every technique I feel like I used just was not, there was always something that was limited to where I could not get it, whether it was a certain column with the HPLC or I can't even list it right now, but there's just always like a little thing that was a problem, and proton was NMR was the only thing that I found like multiple papers on that. Okay, yes, this works.
It really highlights the difficulty of identifying honey food fraud.
Exactly.
I know you can't go back, but at one point you had displayed a spectra calling it a real honey NMR. How did you ensure that this wasn't an adulterated product?
So I was discussing this with Dr. Hellberg, and I was like, I need to find like a real honey. Like I need to compare something against this too. And she was like, oh, that's funny you say that because I actually have one from Cal Poly Pomona. And so she knew it was real, and I trust her instincts. So
She'd gotten it from the source then.
Yeah.
So what is like the process then with food fraud? So you're like, I can't disclose that now, but like once you have the NMR data that's more conclusive, like these are adulterated, like I know you're gonna try to publish something, do you like contact those companies and say like, hey?
I feel like Amanda would know more about that.
Yeah, you have to get like a written consent that you're allowed to like test their materials for you to be actually able to like put their name out there. So unless you want to like contact everyone. Yeah.
Fantastic presentation, by the way, Vanna. I was gonna ask, did you face some challenges with NMR for all of the trials, like all of the different honeys, or were some more than others?
Some are more than others. It was weird because like I would be running the samples and they'd be going well, and then like I'd hit a sample where it like we just get that ugly bump. And I'm like, oh, like why is this happening? So it really varied.
Great job.
Oh,
Okay. Sorry, not just gonna
No,
show
you're
you
good.
We still have maybe 2 more minutes if that needs any lingering questions on that. Yes.
How do you tell the difference, or like, what is the difference between?
Here's what I found.
Nobody
Go for it.
Grade A versus grade B, what's the difference?
There's not much of a difference. I think it's something to do with the moisture percentage as well. I'm still trying to look into it. They're pretty like, it's very like similar though. Like they're not.
It's one more. Yes.
And why again did you specify clover and wildflower as opposed to any others?
When I was doing literature search on what type of honey I wanted to do, I didn't find as much with clover and wildflower. So I was curious to see like what I was going to find, because I did find a lot of cases with Manuka honey, and that was with the substitution with less expensive like honey. So I was like, okay, well, do something that not really known would be cool.
Great, let's give Vanna. Thank you all so much for your patience and also kind of sitting through the entire seminar. We are on to our very last presentation for the day. Our presentation is also food chemistry, maybe food biochemistry, if you will. But Amanda will be talking about using DNA barcoding to identify species of raw, ready-to-eat seafood products. So in Orange County, and with that, Amanda, take it away.
Yes, so as Dr. Agma said, I'm going to be looking at use of DNA barcoding to look into different species of raw ready-to-eat seafood. I know we've been talking about chemistry a lot today, but we're going to go into the molecular biology side of things right now with mine because I'm biochemistry. So let's get started. So I just want to give you a quick overview of my presentation. So first, we're going to be talking about the background information of my project and the prevalence. Then I'll go into the methodology of how I actually went through this research, and then we'll go through my results and conclusions. So for my background information, some of you might be wondering what raw ready-to-eat seafood is. And I wondered that to begin with because I was just like, I heard sushi and I was like, I'm in for this project. So raw ready-to-eat seafood is food products that actually lack a heat treatment. So our three products that we used were ceviche, sushi, and poke, which are all, when you get them, they're raw fish. So that's just a quick definition. So my introduction, so previous research actually has been done by Oceana, showing that 55% of seafood from sushi restaurants were actually mislabeled. So 55% is obviously a little bit more than half, which is a lot. And then also prevalence of the study. So seafood mislabeling actually happens around the world and of course in the United States. And also it's used by the FDA, the CO1 region, which I'll talk about a little bit later, is what we actually amplify to get the species to actually compare it to what's on the actual menu. And when I'm thinking about the three things that I care about most when I hear substitution of fish, is obviously first, some fish are more expensive than others, which we will go into later. So the consumer is paying for something that they're not actually getting. So they're paying for something, not my vibe. And then second of all, obviously the mercury content. So mercury, there's different amounts of mercury in each fish. So you might be getting a fish that has a lot more mercury than you think, which is very dangerous for younger children and pregnant women. And the third thing is when you do this, there might be more parasites or different bacteria that are in these fish species that we don't know about. So let's go through my methodology of how I did this research. First, we collected 105 samples from different restaurants around Orange County. Then we DNA extracted it, put it through PCR to actually amplify that CO1 region, and then we did 91 samples of sequencing. We did 91 instead of 105 because 14 of those samples did not pass QC, so we couldn't use them for sequencing. This is a DNase blood and tissue kit, which is what we used for DNA extraction. My lab partner said this very great. We measure out the amount that will get stuck in your teeth, so about 10 milligrams is what we measure out of each fish sample, and then we put it into like a grinding thing. We basically lyse the cells to get the DNA out, and then we actually put it into a silica column to get all the debris and leave us with the DNA. I also want to touch on the CO1 region we've been hearing me talk about. So the cytochrome C oxidase unit 1 region. This has been used to actually compare the species of what the fish is to what it says on the menu. And it's a 655 base pair region of the DNA of a mitochondrial DNA. This is really easy to actually get out, and we know we're going to get it because there's about 1 to 1,000 copies of this gene, of this mitochondrial DNA per cell. So if you think per cell, lots of cells in the tissue, we're going to obviously get this. And plus it's less expensive, which we all want, because all we have to do is get the primer pairs, which are about $20 each. And we have those for a long time. So through PCR, first, we obviously have our master mix as the template DNA, the magnesium chloride, the DNTPs, and our primers. We're gonna denature the strand, anneal our primers on, and then we're gonna extend those and have our amplification of this CO1 gene. Here's a picture of me and my lab mate Courtney, and we're actually looking at a gel to get these bands from the PCR. If we do not see these bands, we do not use them in the sequencing, mostly because waste of money, and because if we don't get a band here, it's not going to show up in sequencing. So we're going to have to do mini barcoding, which is really just getting primers that are going to go closer into that region, because PCR loves to amplify smaller regions of DNA. And instead of BLAST, if you guys have probably heard of that, we use this sequencing thing called BOLD. And it's just more specific to actually what we're looking into. So the cone-1 gene, lots of gene banks from all these research papers are actually going to be put into the system, and all we have to do is put our data sequence in a DNA sequence into there from each sample, and then we'll get this lovely result. So we actually get the species and genus from the sample that we got, and then we're able to pull that out and compare it to the menu. I want to point out the similarity, which there's a, I don't know how to use that pointer thing, but the similarity percentage is actually how, so once we put in the DNA sequence, this is how similar this is to that genus and species that it comes back to us with. So let's go through our results and conclusions. So here is every single one of the species that we tested for when we went through all the poke, ceviche, and sushi samples. As we can tell in the green, we have a bunch of them that are acceptable market names 100% of the time that we tested them. So like albacore and mackerel, when we tested them, they came back as the species that they said they were. Now I do want to point out the unacceptable market names, which is in blue. A lot of it is in fish. It just means that they weren't specific enough when they actually told us what was on the menu, or what was on the menu to what it actually came back as. And then substituted species is actually the species is changed out for another one. So I wanted to, instead of putting all of my samples up on here, I just wanted to point out a few that I thought were stood out, or people asked me a lot of questions about when I did poster presentations. Salmon for Atlantic salmon. So this is considered unacceptable market names because the FDA wants you to be more specific with the actual fish species. So when you just say salmon, they don't like it. We have to call it unacceptable market name when we look at the FDA fish list. And then we have fish, which is most of the time when we got ceviche, it was fish or white fish. And when we actually asked the people in the restaurant, they didn't know what species it was. So that's kind of concerning to me because I would like to know what I'm eating. And so we just want them to be more specific when they actually say it on the menu. Then we have the two standout ones that I think were for substituted. So first there's red snapper for tilapia. There has been many studies shown. A study that I read was that 9 samples that they tested out were all substituted for red snapper. And so red snapper is about twice the price of tilapia. So again, consumers paying for what they're not getting. And red snapper actually has a lot more mercury in it than tilapia does. And the one that stood out to me the most that I was kind of like, when I saw it, was that tuna for capelin. So it was a ground up tuna sample. So like all you see is red fish meat ground up. Capelin is a type of smelt, which is like anchovies like looking things. So definitely not tuna. And then, so here are concluding results. So 86.7% of our ceviche samples were mislabeled. And as you can see, the unacceptable market name comes mostly from the fish samples that we got, because they didn't say what fish species it was, so we couldn't say what it actually was. And then 72% of our poke samples were mislabeled. This mainly came from that salmon that I was talking about earlier. And then 50% of our sushi samples were mislabeled, and this comes from yellowtail sushi. And because it is substituted, because the vernacular name for yellowtail is burry, so you actually can't call burry yellowtail from the FDA fish list. It's a common name for it, but we're not allowed to use it. In conclusion, this was an amazing research project. I loved it a lot. And for future research, we actually want to see where this mislabeling is coming from, whether it's coming from the supplier or the actual restaurateur, because the restaurateur might be getting this and not knowing it's been substituted before they actually get it. I do want to make a few acknowledgements. So I obviously want to thank my lab group. Dr. Rosalie Hellberg has been amazing during this process, and I am so grateful for her for giving me this project. I also want to thank my 2 lab mates in, can I get it now? Oh yeah. Courtney and Grace were amazing during this project and definitely helped me out. I also want to thank my family, my brother, my dad in the back, love them. Also my friends, and of course the biochemistry and food science faculty and students, and of course everyone in this room for being here. Thank you so much. Any questions?
Thank you, Amanda. That was wonderful. We have time for some questions. Let's start.
This is so enlightening. I really appreciate you. I had no idea. My question is how do we navigate that in the future? Like, how do we stop this? I know that's a huge question, but that's just so crazy.
Yeah, because a lot of papers have been out for like the substitution and or mislabeling, we really want to put it out there to kind of maybe, especially for Mexican restaurants, when you go to a Mexican restaurant, you don't think I'm gonna get raw fish there. Like, so obviously they don't know all the regulations. So maybe just like enlightening people and giving some like more regulations and more things, just put it out there. So people do know, because as you said, you didn't know earlier. So people are actually know that this is going on and help to stop it. So, yeah. That's the question.
Can you talk to us a little bit about the collection method? Because in my head, it's 100 to-go orders of sushi.
Yeah, so I'm sure it's more. So for our collection, some of the samples we did get more than one at each restaurant, especially for like sushi. If you have a mackerel, tuna, salmon, we all got those at the same restaurant. We did go to about like 90 restaurants though, me, Courtney, and Grace. So what we did, said, hi, I would like this to go for my lunch, woo. And then we have a cooler in the back of the car so that it wouldn't get destroyed, wouldn't get spoiled when we're actually going from place to place. So we had to be a little sneaky and just like put it in there. Because as Vanna asked me earlier, we can't say where these samples come from, mostly because then we'd have to ask for permission. So we were just like, we're just gonna put this in the cooler in the back of my truck. Don't worry about it. So, yeah.
You said that there were many cases of mislabeling, and it's USDA? FDA. So how does the FDA not catch these guys when they're putting out names that are right off the bat wrong?
Yeah, I don't know. I would love to know that as well, because I would like to have something in place where like before it hits your like table, it's actually checked. And I'm also working on a thing later on for actually like a UV spec thing that'll say what species it is, which is a lot easier than DNA extracting, setting up for PCR, and then setting up for sequencing, which takes about like 2 days if you're going high speed. So yeah, I want them to put some regulatory stuff in there to actually be able to catch this before it actually hits the consumer. Yes, Vanna?
Did you predict, like, before you ran your samples and got the results back, did you predict, like, oh, I think salmon would be fake, or?
Some of them I did not think, like for salmon, I'm like, salmon is really hard to replicate that with another fish. I was confused why Atlantic salmon, FDA likes it that way. But I also like, I think we got a tilapia sample or something, and you could see like a red stripe, and I was like, or the red snapper sample, red stripe. I was like, oh, it's red snapper, because I've never seen it before, and that's what it is. So red snapper was definitely one that we were thinking that it was going to be, but like I'd never seen it in person. So yeah, a lot of these samples, especially Caitlin for the tuna, never having smoked tuna again, but it's fine.
Yeah. How has this impacted your seafood consumption?
I love me some sushi. Salmon's like my safe bet now. I also like kelp mussels, so imitation crab meat is where I'm at. So.
You know it's an
Can you talk more about those samples that
you were not able to test?
Oh, yes. So a few samples we actually have to go back and do mini barcoding because like either the way the primers went onto the Co1 gene, the species just hasn't, their different species have different things, so it just wasn't able to anneal fully, so it wasn't able to amplify enough for us to do PCR. But when we do that mini barcoding, it's able to actually go in and be used for that. So we're actually doing testing on those right now to get back those samples. So eventually, hopefully, it's gonna be 100%, because right now it's at like 86% like sequencing rate. So.
Wow.
Oh,
jeez. Real quick, the thing you said about the red snapper having high amounts of mercury.
Yes.
It was more than a tilapia.
Yes.
Was it a dangerous amount of mercury or was it?
No, it's just how much, because each species has different amounts of mercury. So I just looked up like how much mercury is in like red snapper versus tilapia. And it's just twice, it's like about twice the amount.
of the tilapia. So like, say it was like switched and you got red snapper instead of tilapia, which is what you ordered, and you were like a young child, then you could possibly have mercury poisoning if you have too much of that. So it just depends if like you're actually eating something that has more mercury than you actually think it does, which is what like some of the things that would go in our mind, like when things actually get substituted. So.
Ready to be out of here.
Yeah, I was like, we can go now. It's totally fine.
On behalf of the Schmid College and all the organizers, I definitely want to thank you all for being here and enjoying this wonderful breadth and depth of conversations around different scientific works. And congratulations again. Let's give a round of applause to all.